Apprehending the foundations of reality is my search. Call me naive or arrogant or both. Still, I persist. I remain on watch for clues or hints about what lies deepest, bedrock reality. That's why an essay written in 1960 by the mathematical physicist Eugene Wigner caught my attention: The Unreasonable Effectiveness of Mathematics in the Natural Sciences. In fact, I keep coming back to it, seeking fresh approaches, implications, challenges. Wigner's starting premise is that the astonishing usefulness of mathematics and the natural sciences, especially in physics, is something bordering on the mysterious, and that there is no rational explanation for it. Mysterious? No rational explanation? That's enough to get me going. How to assess math's unreasonable effectiveness? I seek diverse reactions and responses to this now legendary phrase. What does the unreasonable effectiveness of mathematics mean? I'm Robert Lawrence Kuhn, and Closer to Truth is my journey to find out. Here are my 3 questions. How effective really is mathematics? If really effective, why unreasonable? If unreasonable, what makes it so? Because the unreasonable effectiveness of mathematics has wide appeal among physicists, I think I'll begin with a skeptic, a contrarian who can clarify concepts. I meet a philosopher of science grounded in physics and focusing on quantum theory, David Wallace. David, Wigner's effectiveness of mathematics, to me, packs an emotional punch whenever I hear it. And the key word, of course, is, we know it's effective, so unreasonable. Mathematicians like to think that they're reasonable people, and to say something is unreasonable in terms of its effectiveness connotes kind of a real mystery about the world. First of all, do you agree that mathematics has an unreasonable effectiveness, and how do you proceed to try to assess why?
I'm not sure the effectiveness of mathematics is as unreasonable as all that. Somewhere in the background of that idea is a very Platonic picture of mathematics, where I've got the mathematical objects out in Plato's heaven and the physical objects in the clunky world we live in. And the unreasonable effectiveness is something like, how could claims about the way those mathematical objects are arranged have anything to do with the way in which the crude physical objects are arranged? But in the first place, if we really were just thinking of crude physical objects, some of this is just in the nature of the way those things are arranged. If I have 5 marbles and then a further 3 marbles, is it so unreasonably effective that I can use arithmetic to work out that I have 8 marbles? You know, marbles just instantiate the structure of the natural numbers. In physics, to a much higher degree, similar things are true. I can't even start telling you what the content of a physical theory is without using a huge amount of mathematics. So the mystery, if there is one, the unreasonableness, if there is one, is not really, given that things are arranged in certain structures that we use math to describe, that they indeed behave the way math says. The unreasonableness, I suppose, is how is it that we have this kind of structural framework as a way of describing and talking about things.
Because if we're able to discern it, it has to have that relationship, or we wouldn't have even done it. Is that the point?
Something like that. I mean, look at it this way. Even in our ordinary, everyday world of chairs and tables and cats and dogs, then we can still describe that in a certain mathematical structure. That math is so intuitive to us because we evolved with it, that we don't notice that it's an abstract mathematical framework, but it's really set theory and arithmetic and things of that kind. It's just as unreasonable in that sense that we could have a world of objects and properties as it is that we could have a world of the weird and wonderful things of quantum mechanics.
Whether it's Maxwell's equations or the inverse square law in gravity or Einstein's refinement of that, they're fairly simple kinds of relationships. And it, to me, can be startling that the world exactly fits that small equation rather than being like an irrational number along the number line.
I think it is remarkable that the world can be described so effectively by such simple pieces of math, but I don't think that's so much the unreasonable effectiveness of mathematics so much as it's, if you like, the unreasonable simplicity of the universe. Perfectly well have been that the universe was just an extraordinary chaotic mess, with no simple principles governing it at all. The fact that we have these extraordinarily simple, unified principles, I do think is remarkable. And if we didn't have it, we wouldn't be able to understand the world to anything like the depth we have. But look at it this way, the world could be described by hideously complex math. But that's not so much why is the world described by math, it's why is the math that describes the world so simple? Why couldn't it have been hideously complex and ununified?
Yeah, but your point is that that's the result of the world, not the math. I understand that, but it's still a question.
Yeah, why is the world so simple? I don't know the answer to that question.
To David, it is not so much the unreasonable effectiveness of mathematics as it is the unreasonable simplicity of the universe, such that simple math can describe it. I can buy that, but still there seems something big-time unreasonable going on. So, who might take a different stance, an opposite approach, wondrous of the explanatory potency of math? I'd bet on a pure mathematician. I go to Boston to meet an expert in algebraic topology, Harvard's Michael Hopkins.
The Wigner essay is a fascinating essay. It sounds from the title like it's going to be a love letter to mathematics, but he's in fact raising a different question. And in it, he talks about the effectiveness in mathematics as being like you're walking down a corridor of locked doors with a big key ring, and every time you try to open a door, you guess right on the first or second try. And I think in a way, in modern parlance, he's asking the question, is mathematics so good at describing phenomena because what we label as phenomena suffers a selection bias? I guess I like to think about when we think about a phenomenon, when we describe phenomena, there's three aspects to it. There's the phenomena, there's a story we're telling ourselves about the phenomena, and there's a model, an abstract model we have in mind.
You talk about a selection bias.
So we become aware of phenomena when we interact with it. And in interacting, we tell ourselves a story about it. But there could be things out there that are important to the universe that are so chaotic that our minds can't manufacture a story or an abstraction.
So that's like saying the unreasonable effectiveness of mathematics is because we are selecting the kinds of phenomena that mathematics can be effective for, as opposed to the unreasonable effectiveness of mathematics that can do everything and anything.
Well, that is, in some sense, the question Wigner's raising in that essay. But I think mathematics is effective because the model, the abstract model that we're making, is often applicable to something completely different. And the abstract model itself often has an unreasonable kind of richness in structure. There's a rich relationship between my field of research, algebraic topology, or the subspecialty of homotopy theory, and condensed matter physics. So physicists are studying matter that's at a very low temperature, so that in order to, like ice, right? You may have frozen ice into some shape, and to get it into a different shape, you have to put a lot of energy in the system to change its state or its phase. And so physicists are interested in studying the phases of materials. Mm-hmm. And that turns out to be something that one can approach through algebraic topology.
Because you deal with transformations. Transformations is a core element of algebraic topology.
Yes, transformations and algebraic topology has a long history of dealing with mathematical objects that we don't know up to infinite precision. And so the residual quantities that you can use to describe those are useful in any physical situation where you've specified the situation up to some error. You may have controlled the error, but it's been specified and only up to error. And so ice looks like ice at certain temperatures. If you raise the temperature a lot, it will change into water. And in condensed matter physics now, through the work of many, many people, there's a role for algebraic topology in classifying phases of matter.
Michael makes 2 points that refine math's unreasonable effectiveness. First, a selection effect, where the abstract models we choose have an unreasonably rich structure. Second, ideas in pure math, which are good at elucidating rich structures. The remarkable progress of scientific explanation is thus rooted in building abstract models of reality, which are conducive to mathematical analysis. But do all areas of science qualify? Where might math's unreasonable effectiveness falter? Are there new testbeds, exceptions, challengers, defeaters? I go to the Santa Fe Institute to meet a complexity biologist known for his iconoclastic visionary views, Stuart Kauffman.
So Wigner cast upon the world this amazing phrase, the unreasonable effectiveness of mathematics, and it's spectacular in physics. The question is whether or not we should be overwhelmed by his claim, and I think the answer is absolutely no. So if we think about the evolution of the biosphere, of biology, I am now falling in love with the phrase, the reasonable uselessness of mathematics. Could you have written down an equation for the becoming of all of these ways of making a living in the biosphere? The answer is no. There's no mathematics for it.
Well, theoretically, one would say if you knew how to describe every single particle and all their dimensions and the quantum probabilities, it seems impossibly large, but it is finite, and you could do that.
No, but here's why.
In principle.
Sure.
You're saying in principle you can't.
Yeah, and here's why. You know, it's a huge 6n dimensional phase space. It's a really big one. How would you pick out as relevant variables? There is no way to specify the collective degrees of freedom that are relevant to the becoming of the biosphere. None. You can't get to the relevant variables that have to do with the evolution of the biosphere.
So your claim is that when new functions appear, they are not being able to be described by pre-stated laws or mathematical descriptions, but once they do appear, then mathematical descriptions of their dynamics, how they interact, are perfectly fine.
Yeah.
So it's that origin moment.
It's the origin moment of ever new functionalities in the becoming of the biosphere. We do need to defend the word function. Ever new functions arise in the evolution of the biosphere. They arise in the evolution of the economy. There were not cell phones 1,000 years ago, and people did pretty well. Once there's cell phones, there's apps on cell phones. What is actual now enables the adjacent possible of what can become. You cannot restate it. We are sucked into the opportunities we ourselves unknowingly create, and so is the biosphere. So it's an entirely new way of thinking about the becoming of things.
That I'm struggling between, is that true in principle? Or is it true because it is so large it's uncomputable?
I think it's true in principle. To write down laws of motion, you have to be able to say what the relevant variables are. Newton tells us mass and velocity and acceleration and momentum and his laws of motion. What variables would you write down, about the becoming of grizzly bears? What would you write down? You can't.
The fundamental question is it untrue in principle, which is your claim?
I think my claim is the following. An affordance is, this table affords a surface on which we can put cups. These chairs afford a surface on which we can sit. Is there a finite list of all possible affordances of things for uses to do stuff? No. There's just not. It's like the uses of screwdrivers and the indefiniteness of the uses of screwdrivers. You cannot prestate all the uses of screwdrivers. You cannot prestate all possible tasks. The question of what's all possible tasks doesn't make sense. There's no list of it. Yet new tasks, new functions, and so on come to exist always causally. Now, the DNA molecule is more or less classical. The fly is certainly classical. And now it has a white eye, not a red eye. The white eye happens to be fitter in the environment, the consequence of which is that the white-eyed fly, since it's dominant, spreads its DNA within 20 years, so there's millions of copies of that DNA in the universe. How come? Quantum mechanics doesn't explain it. Classical mechanics doesn't explain it. You need the notion of the fitness of the fly in its world. There's no law for that becoming in the biosphere. So there's no law for the becoming in the universe of this strange molecule and this strange organism in the non-ergodic universe above the level of atoms, where almost none of the complex things that could exist will ever exist.
Stu calls out a resounding stop. No, arguing that mathematics does not work, is not effective in the biosphere. His point is potent. If correct, a non-mathematical biosphere would undermine a fundamentally mathematical universe. I'd like to side with Stu. I'd like, with him, to remystify the world. But I'm not there. I'm not convinced that, given a physical world, the biosphere is non-mathematical or incomputable in absolute principle, as opposed to non-mathematical or incomputable in common practice. But what would it mean if everything could be explained by mathematics? I ask a philosopher of science who grapples with the biggest questions, the author of Why Does the World Exist?, Jim Holt.
The wonderful thing about mathematics is that it can describe any possible structure, the structure of the actual world and infinitely many possible mathematical structures of unlimited complexity, unlimited infinities, and so forth. And so mathematics gives us an account of reality that looks as though it's been cleansed of everything that isn't actually in reality. It purges away our perspective on reality, the accidents of our perceptual apparatus, the kind of merely human concepts that we impose on reality. You know, we see a reality that's full of colors and sounds and a flow of time. In the mathematical representation of reality, none of that is present. So when science, using the resources of mathematics, gives us an absolute conception of the world, we're moved to ask, is this what really exists? Is this all that exists? You know, what about the stuff of the world? Mathematics tells us the structure of the world, but it doesn't tell us what the stuff is that realizes the structure. Maybe, you know, mathematics tells us how reality is structured, but the stuff of reality is something like consciousness, or it's something like perceptions. And so, what does this have to do with the unreasonable effectiveness of mathematics? Mathematics tells us about one aspect of the world and is completely silent on another aspect of the world. And by the way, yes, mathematics is extremely effective when we're dealing with the most fundamental level of reality, but it's pretty hopeless at explaining, for instance, what you're going to do later today. So mathematics is very effective in the domain of reality in which it's effective. But that's not all of reality. That's actually a very small part.
But even at the fundamental level, I mean, the argument is that we're imposing mathematics on the world because it's our way of understanding it, and we're developing models of reality with mathematics that are approximations.
I mean, there are those who believe, like Sir Roger Penrose, believes that the world is, in a sense, really made out of mathematics. Hartree Field argued that you can do all of science without positing any mathematical entities, that it's very convenient to use mathematics to do science. So these are the two extreme positions. And in that the continuum of positions in between, I would feel more comfortable being away from Sir Roger Penrose, because his belief that the world is made out of mathematics is a kind of reflection of Plato's idea of reality, and I think that's a beautiful conception, but I think it's slightly religious, and I prefer to stick with a more hard-headed empiricist.
Jim describes how a mathematical description of the world purges it of human perceptions. I like that, but is it for the better or for the worse? One cannot go wrong with hard-headed empiricism, in the sense that all discoveries will be true, But do we exclude truths not discoverable by empiricism? Do we leave revelatory gold on the explanatory table? I ask a visionary scientist unwilling to reject the role of the human mind in the nature of reality, unafraid of the deep waters of teleology, mind, and meaning, physicist Paul Davies.
The mystery for me is not why does mathematics work in the world, but why does mathematics that human beings have the ability to understand and manipulate work so well in the real world? Why is it that this species, Homo sapiens, has evolved the capability of doing this type of abstract reasoning and doing these mathematical procedures, some of which are quite hard, in a way that is so extraordinarily effective in grasping the nature of so many physical phenomena? Now, a lot of people just shrug this aside. But I don't think there's anything in our evolutionary history that compels human beings to develop the cognitive architecture necessary to do this. Our brains, our minds have evolved, like our bodies, to survive in the proverbial jungle. And so, of course, it will be useful to be able to count and work out angles and so on. But there's absolutely no reason why we should have the level of mathematics necessary to explain, for example, the nature of black holes or the structure of the hydrogen atom or anything like that. These are things beyond any sort of reasonable survival value. So is it just a coincidence that the mathematics that we evolved to cope with just for basic survival also just happens to work so well in so many areas of reality? I don't believe in coincidences like that. I think it means that the human mind has evolved, and the mind, not the brain, I'm talking about the human mind has evolved to somehow mirror the nature of reality in a very deep way. I think it's a non-trivial fact. It sounds a little bit mystical. It sounds like somehow we are meant to be here, or that we are players in the great cosmic drama in this very fundamental way. Yes, I think we are, and it's one of these facts that I regard as giving huge significance to human life.
You are distinctly in the minority among at least the physicists and mathematicians and scientists, a place that you apparently like to inhabit.
Yes, I freely admit that most of my colleagues would not agree with me. On the other hand, they don't give very coherent accounts of why mathematics is so useful in physics either. And so I often will provoke them by saying things like, well, where did the laws of physics come from, and why do they have this elegant mathematical form that they do? And they really don't have an answer to that, because I think there is something about the emergence of life and intelligence that plugs into this deep nature of reality. So you're seeing this as a sort of quasi-religious view. It's very far from traditional religion, but it is a belief that in this great scheme of things, human beings are one representative of this deep place that life and mind has in the unfolding scheme of the universe.
So you have taken the unreasonable effectiveness of mathematics as a deep probe of what reality is and sees more meaning and purpose in the totality of realities.
I don't like brute facts, but so people can say, well, that's just the way the world is, but I want to know, well, why is it that way? And I just think this connection between our ability to describe the world through human mathematics must say something very profound about the nature of the human mind. And so this is built very deeply into the structure of the universe, I claim.
Eugene Wigner concludes his essay, The Unreasonable Effectiveness of Mathematics and the Natural Science, with optimism. We should be grateful for it and hope that it will remain valid in future research, to our pleasure, even though perhaps to our bafflement. Bafflement is a treasure. It challenges conventional wisdom and stimulates fresh thinking. So what to make of our bafflement at math's unreasonable effectiveness? Perhaps what's really unreasonable is why the world is so simple, such that math can work its magic. The abstract models we select have an unreasonably rich structure which math can elucidate. Does math's effectiveness stop, halt, at the boundary of the biosphere? Mathematical descriptions purge the world of human perceptions. That we can describe the world through human mathematics links the human mind with the deep structure of the cosmos. That's what I'd like to believe. I'd like to believe that we humans are somehow special, and that's why our human mathematics is unreasonably effective. But I warn myself, don't believe it too quickly to be closer to truth.
For complete interviews and for further information, please visit closertotruth.com.